Hi, hola, bonjour, and Salaam. Welcome to Blueprint Bazaar. In this bonus video, we're shifting gears from mechanical assembly to something equally critical for real-world manufacturing, creating a complete and accurate bill of materials, or BOM, for the plastic shredder machine using SolidWorks. A BOM isn't just a table, it's the backbone of your entire project when it comes to fabrication, procurement, cost estimation, and assembly workflows. No matter how perfect your 3D model is, if the BOM is incomplete or inaccurate, the entire production process can run into serious issues. We start by opening the final assembly of our shredder machine, which includes everything we've built across the previous parts: frames, shafts, blades, spacers, gears, bearings, and fasteners. From here, we transition into the drawing environment, where the BOM will be generated. SolidWorks makes this process efficient, but it requires thoughtful setup to ensure the output is usable and clear. The first step involves placing a drawing view of the full assembly onto a sheet. This acts as the anchor point for the BOM table. Once the view is positioned, we navigate to the table menu and select Bill of Materials. Instantly, SolidWorks populates the BOM based on the assembly's structure. It lists each part, its quantity, and default properties like part number and description. But this is where many users stop prematurely. A truly functional BOM needs more than just a generic list. It requires customization. So, we dive into editing the column headers, adding or adjusting fields like part number, description, quantity, material, and possibly weight or supplier if needed. For example, instead of a vague Part 1 or Part 3, we ensure every item has a functional, readable name, like rotating blade 8 hole or spacer 5 millimeters. We also walk through how to link each column to properties inside the part files. If you've set up custom properties within your parts, such as material type, thickness, finish, or manufacturing process, these will auto-populate into the BOM. If you haven't done this yet, no worries. This video shows you how to quickly add them retroactively. One major point we address is the difference between structured and flat BOMs. A structured BOM reflects sub-assemblies exactly as they're built in the CAD hierarchy, which is helpful for organized assembly steps. A flat BOM, on the other hand, lists all components as a single-level list, regardless of sub-assemblies. Depending on your fabrication approach, whether you're manufacturing in-house or outsourcing parts, you'll choose one over the other. We also discuss how to handle common issues, like duplicate parts, missing descriptions, or incorrect quantities. SolidWorks automatically counts instances of a component, but if an assembly has flexible or mirrored configurations, double-checking is key. Miscounts in fasteners, spacers, or bearings can lead to headaches during the physical build. As the BOM takes shape, we spend time styling it for readability. This includes adjusting column widths, font sizes, and table alignment on the drawing sheet. A clean, readable BOM isn't just nicer to look at. It reduces miscommunication between designers, fabricators, and purchasers. Another important section of this video explains how to export the BOM. SolidWorks allows you to save the table as an Excel spreadsheet or CSV file. This is extremely useful for sending the BOM to suppliers, integrating it into ERP systems, or calculating costs. We demonstrate how to export, double-check the data, and make small edits directly in Excel if needed. We also take a moment to point out common mistakes, like forgetting to include hardware from the SolidWorks design library. In Part 18, we added ISO standard bolts and screws into the assembly, and those show up in the BOM automatically. This reinforces why it's important to fully complete the digital assembly before generating the BOM. Anything left out won't be counted. For those following along with the goal of fabricating the shredder, this video highlights the bridge between design and production. The BOM ensures you're ordering the correct number of blades, the right spacer thicknesses, proper shaft lengths, gear sizes, and correct fasteners. Nothing more, nothing less. This process isn't limited to the shredder project either. Whether you're designing machinery, furniture, enclosures, or consumer products, the ability to generate and control a BOM is a vital skill. It's the language that translates your 3D model into real-world materials and components. As the video progresses, we touch on BOM updates. If you change a part inside the assembly, say replacing a spacer or modifying the frame, the BOM updates dynamically. This is a huge advantage of a parametric CAD system like SolidWorks. We show how to force refresh the BOM, update quantities, and double-check for consistency. This dynamic linking between the assembly and the BOM is what makes parametric design so powerful. Any dimensional change, material swap, or component replacement inside the 3D model instantly reflects in the BOM, reducing the risk of manual errors and miscommunication. For instance, if you decide midway to change the thickness of a spacer from 5 mm to 10 mm, not only does the model update visually, but the BOM will also reflect the updated part name, description, and even weight if those properties are linked. We also dive deeper into managing configurations within the BOM. Let's say your shredder has optional features, like a reinforced hopper or alternative side plate designs. SolidWorks allows you to create multiple configurations within the same assembly file, and the BOM can be tailored to show the correct set of parts for each configuration. This is particularly useful if you're preparing versions for different clients or testing design variants. Additionally, we explore how to handle suppressed components. Sometimes, parts like temporary supports, reference geometry, or optional hardware are present in the assembly but not meant for the final build. SolidWorks gives you control to exclude these from the BOM without deleting them from the model. This keeps the design workspace intact while ensuring the BOM remains clean, accurate, and production-ready. We also take time to cover how custom properties play a vital role in generating a fully informative BOM. Properties like material, weight, finish, vendor, part number, and manufacturing notes can be embedded directly into each part file. When you insert the BOM table, these properties automatically populate, creating a document that isn't just a list of parts, but a full specification sheet that anyone from procurement to the shop floor can use. For example, when selecting bolts from the SolidWorks design library, each ISO standard fastener comes preloaded with critical metadata. If you've been following along from Part 18, where we added fasteners into the mounting and side plates, you'll see how those parts now show up in the BOM with size designations, standard numbers, and quantities, all without additional manual input. This level of automation cuts down hours of administrative work while improving accuracy. Another crucial aspect we highlight is how the BOM layout can be customized for your specific needs. Maybe your fabrication team wants a simplified BOM that only lists item numbers, descriptions, and quantities. Meanwhile, your purchasing department might require one with detailed vendor information, weights, and material grades. SolidWorks allows you to configure different BOM views, either on the drawing sheet or exported to Excel, matching the requirements of each department. Furthermore, we explore how hierarchical assembly structures influence the BOM. You'll learn the difference between a top-level BOM, which only lists sub-assemblies, and a parts-only BOM that breaks everything down into individual components regardless of their sub-assembly status. This distinction is crucial for manufacturers deciding whether to outsource sub-assemblies or handle everything in-house. Equally important is handling phantom assemblies. These are grouped components that exist for organizational purposes but are not physically assembled as separate units in manufacturing. We demonstrate how to mark these as phantom so that SolidWorks knows to dissolve them into the BOM structure, ensuring all child components are listed individually without showing the phantom assembly as a separate line item. We also touch on error prevention techniques. It's common for designers to accidentally omit parts from the BOM by forgetting to fill out key properties in the part files. In this video, we show you how to set up property templates and enforce required fields so that every part created in your shredder assembly meets a minimum documentation standard. This is a professional workflow technique that pays off massively when scaling your project or collaborating with larger teams. Another helpful feature we showcase is how to link mass properties directly into the BOM. By assigning the correct material to each component in SolidWorks, the software automatically calculates part weights. This becomes invaluable for logistics, costing, and structural checks. You can display total weight per item or even a grand total for the entire shredder assembly right inside your BOM table. This way, you're not just designing visually, but also engineering with precise physical data. Additionally, we demonstrate how to reorder items, adjust balloon callouts, and sync the BOM with the drawing views for clarity and ease of understanding. This step ensures that when your workshop receives the manufacturing drawings, every part number in the BOM matches the numbered balloons on the exploded view or orthographic drawings. We also dive deeper into how SolidWorks drawing features complement the BOM creation process. Specifically, we cover how to generate detailed 2D drawing sheets directly from the 3D assembly. This includes setting up standard views like front, top, isometric, and section views to visually communicate part geometry. Once the BOM is placed on the drawing sheet, you can easily create exploded views with automatic balloon annotations. These balloons dynamically link to the BOM, ensuring that each part on the drawing corresponds perfectly to its row in the table. Furthermore, we explore how to use section views and detail views in drawings to highlight complex areas like the blade stack, bearing mount, or gear assembly. These focused views are not just cosmetic. They offer precise dimensional clarity to fabricators who rely on your drawings for cutting, machining, or assembling. We also show how to apply automatic center marks, hole callouts, and dimension annotations, streamlining the drafting process while maintaining engineering accuracy. Additionally, we explain how custom title blocks, revision tables, and company logos can be embedded in your drawings, giving them a professional touch. You'll also learn how drawing sheets stay parametric. If the assembly updates, the views, BOM, and even callouts automatically refresh without manual intervention. This drastically reduces the risk of sending outdated or incorrect documentation to manufacturing. Beyond the basics, we also walk through how to manage sheet formats and templates in SolidWorks drawings. Whether you're working with A4, A3, or larger sheet sizes, SolidWorks allows you to customize the border, title block information, and proprietary fields like part numbers, designer name, date, material, or revision status. These sheet formats can be saved and reused across all future projects, ensuring consistency throughout your documentation. A key focus is on dimensioning standards. We demonstrate how to apply smart dimensions that automatically snap to edges, holes, and features, following ISO, ANSI, or your preferred standards. We also show how to manage tolerances, whether you need general fit tolerances or detailed GD and T geometric dimensioning and tolerancing. This is crucial for assemblies like the plastic shredder, where precise clearances for blades, spacers, and shafts determine the machine's performance. Another feature we highlight is annotation management, such as adding weld symbols, surface finish symbols, center lines, and hole callouts. These annotations aren't just visual. They communicate vital manufacturing information. For example, if a part requires a machine surface finish or a chamfer on a sharp edge, these details are embedded directly into the drawing for machinists to follow. We also dive into exploded view drawings, which are particularly useful for assemblies like this plastic shredder. Using the exploded view tool, we generate clear, sequential assembly steps. Combined with auto-ballooned BOMs, these drawings become highly valuable for fabrication and assembly teams, especially when dealing with dozens of repeating components like blades and spacers. Moreover, we explore detailed views and broken-out sections that zoom into critical parts of the assembly without cluttering the main drawing. For example, a detailed view of the bearing housing or gear alignment can be shown separately with enlarged dimensions and specific callouts. This part of the video reinforces that SolidWorks isn't just about 3D modeling. It's a complete engineering communication tool. By combining assembly-level BOMs with fully detailed 2D drawings, you create a manufacturing-ready package that minimizes errors, reduces back and forth with fabricators, and speeds up production. Exporting is another critical step, and we demonstrate best practices for generating PDFs, DXF files for laser cutting, and DWG files for CNC machining or fabrication teams. We discuss line thickness settings, layer controls, and how to ensure your exported files meet the standards used by manufacturing partners. We even touch on watermarking, or adding for review-only stamps for draft versions. Additionally, we highlight the importance of using section views and auxiliary views for showcasing complex geometries, especially for the shredder's internal mechanisms like the blade-to-shaft interfaces, bearing seating, or gear meshing zones. These views are critical for machinists and fabricators to understand how each part should be manufactured and assembled. By the time we wrap up this drawing segment, the goal is clear. You're not just producing pretty diagrams. You're generating precise, professional engineering documentation that communicates exactly how the plastic shredder, or any mechanical assembly, should be built. This step transforms your CAD model from a virtual concept into a manufacturable, real-world product. Please keep supporting us as we dive deeper into mechanical design and development. Don't forget to like, share, and subscribe so you never miss a step on this engineering journey with Blueprint Bazaar.